Hi, welcome to this video on project 1, which is a project on the percolation problem. In this video I'm going to explain the problems in the project, and I'll also give you some hints along the way on how you go about solving these problems. The goal of the project is to write a program to estimate the percolation threshold of a system. So what do we mean by that? So we are given some kind of a porous material or a porous medium that we are going to model as a two-dimensional grid. All right. So here is an example of a 4x4 percolation system, which represents some kind of a porous material. Now, what we are interested in is how porous does this material have to be for it to percolate? Meaning, if we pour something, some liquid here at the top, for the liquid to appear here at the bottom, right? So, how many cells here have to be open for the system to percolate? So that's what we refer to as the percolation threshold. All right. So we could think of it as follows. So here on this graph, on the x-axis, I'm showing you the extent to which the material is porous, which is denoted by P, which simply represents the fraction of the cells in this grid that are open. And then on the y-axis, we plot the probability of the system percolating. So we'll just write percolation probability. Right? And we are interested in the transition point, the threshold. So the system remains like non-percolating for small values of P, and at some point it transitions from not percolating to percolating. All right? And it's this transition point that we are interested in, which we are going to denote by P star. So what is this value of P star? Which is a number between 0 and 1, because it is after all a fraction or a probability. So it's a number between 0 and 1. So we are interested in what this value is. So it turns out that there is no mathematical solution for this problem. So we have to resort to computational means to figure out what this value P star is. And that's exactly what we're going to do in this assignment. We're going to write a program that will give us a very good handle on what P star is. Okay. Now, when you download the zip file for the project from this URL and unzip it in some folder, you're going to see various files in there. You're going to see the project specification itself, which is that, and then you'll also see the starter files for the project, which are percolation.java and percolationstats.java, and you will be fleshing out these two files. Okay, and then you'll also see a test script called run test that you can run to make sure that your programs meet the input and output specifications. And then in addition, inside of a folder called data, you'll see a whole bunch of test data and reference solutions that you should use to test and debug your programs. Okay, and finally, you also have what are called visual clients that you can use in order to test your programs. And then there is a template that is given to you for writing your reports, right? So do write your report using this template. Okay, now before I proceed, let me just say that this checklist or this video is going to be useful only if you have actually read and understood the project specification. All right. So before you proceed, with this video, please make sure that you have read the project specification well and that you understand the problems in some detail. Only then this checklist, which is this PDF and this video, are going to be helpful. Okay. All right. So the first problem is to model a percolation system, and for that, what we're going to do is we're going to create a data type called percolation. Okay, that supports this API shown here. All right, and percolation.java is the starter file that contains this data type definition. So that's the file that you need to modify, and you basically need to implement this data type in that file, and the data type needs to support this API. So let's go through the methods in the API. So it's the constructor that lets you create an n by n grid, which models a percolation system as a 2D array, right, as an n by n grid. And initially, all sites are blocked, right? And then this method here is an instance method, open, that takes I and j as arguments, and then it's supposed to open the site ij, right, if it is not open yet. Okay, and then this instance method is open, takes I and j as input, and it's supposed to return true or false, suggesting whether that site is open or not. And then this method here is full, tells if a given site ij is full or not. Okay, and this instance method is supposed to return the number of open sites in the percolation system. And then finally, this predicate method is supposed to return true if the system percolates and false otherwise. Right, so that's basically the API, and these are the methods that you will be implementing inside of the percolation data type. Okay, now we are going to model the percolation system as an n by n grid of booleans. Right, it's a two-dimensional array of size n, and a cell, and it's an array of booleans, and a true cell is going to denote an open cell, and a cell that is false is going to denote a blocked cell. Okay, so when you initially create a percolation system, all the cells are false, meaning they are all blocked to begin with. Okay, so that's how we model a percolation system, simply as an n by n array of booleans. And then we can, just with this array of booleans, we can certainly implement all the methods in the API by simply scanning the array directly. Okay, that's certainly possible using nested loops and whatnot, but that approach is fairly inefficient, and it certainly does not meet all the performance requirements that are suggested in the project specification, right? Instead, what we will do is we'll implement the API quite efficiently using what is called the union find data structure. All right, so that's what you're supposed to do in this project. Use the union find data structure to implement the API. Okay, now for a percolation system that is represented as an n by n array of booleans, we're going to use an object of type UF or union find with n square plus 2 sites. Okay, so we're going to establish a mapping between the two-dimensional array of booleans and a union find data structure that has n square plus 2 sites. All right, now and we do that because we want to use the union find data structure to implement this API, right? So we have to have a UF object to go along with the 2D array of booleans. Okay, and each cell in the 2D array is going to correspond to a site in the union find object. Now the problem is that in the two-dimensional array, you refer to a cell using 2 numbers, an I and a j, right? Whereas in the union find data structure, each site is just referred to using 1 integer, all right? And hence, what we need is some kind of a method that would map a cell from the 2D array to a site in the union find data structure. And that is going to be done by a private helper method called encode. Okay, so this is something that you need to implement inside of percolation, right? So you will see a helper method in there called encode that you need to flesh out. And it's a very simple method. It's basically a one-liner. And it's going to be a simple formula that involves n, I, and j. And that formula needs to be written in such a fashion that when I and j are 0 and 0, the method is supposed to return 1. When I and j are 0 and 1, it's supposed to return 2. And when I and j are n minus 1 and n minus 1, it's supposed to return n square. So you need to write this formula in such a manner. Okay. Now, so here we said that the union find data structure needs to be created with n square plus 2 sites. But there are only n square cells in the 2D array. So why this additional, the 2 additional sites? Well, one site is going to be called the source. So it's a site in the union find data structure that is non-existent in the 2D array. And we're going to call that a virtual site or source. And that's going to have a site ID of 0. And then there is another site that we're going to call a sink, which is also virtual, meaning it's part of the union find data structure, but it's not part of the percolation system. And that's going to have an ID of n square plus 1. Okay, so the site ID 0 and n square plus 1 are reserved for the 2 virtual sites, the source and the sink. Okay, and we'll see the need for these virtual sites. It's basically these virtual sites are having them that helps you implement these methods fairly efficiently, right? Okay. So here then is an example of a 3x3 percolation system. So n here, n in this example is 3. All right, so I goes from 0 to 3 and j goes from 0 to 3. Okay, and the corresponding union find data structure is shown here. So a cell here maps to a site ID here. So 0, 0 is mapped to 1, 0, 1 is mapped to 2, 1, 0 is mapped to 4, and 2, 0 is mapped to 7, and finally 2, 2 is mapped to 9. Okay, so that's the correspondence between a cell in the percolation system and a site in the union find data structure. And here are the 2 virtual sites. So you have the source with the ID 0 and the sink with the ID 10. Okay, for this 3x3 system. And again, notice that the source and sink, they're only part of the union find data structure. They're not part of the percolation system itself. Okay. Now let's talk a little bit about the instance variables that you will need inside of the percolation data type. Well, you will need you need a variable called n of type integer to store the percolation system size. So that's one instance variable. Then you will need an array of booleans, a 2-dimensional array of booleans. Let's call it open. And then you will need a variable called open sites to keep track of the number of sites that you open in the percolation system. And then finally, you need an object called UF that is an object of type union find data structure, right? And the particular implementation of union find that we're going to use is called weighted quick union UF. So this variable UF is going to be an object of that type, right? So these are the instance variables that you need minimally to implement the percolation data type. Okay. Now let's talk about how you would implement the constructor. So in the constructor, the first thing you need to do is initialize all the instance variables that we just talked about, initialize them appropriately, and initialize the 2D arrays such that every site in there is, every cell in there is blocked to begin with, meaning it has a value of false. And then what you need to do is you need to connect the sites or the cells corresponding to the first and last rows of the percolation system with the source and sink sites respectively. So this is the first row of a 3x3 system, and this is the last row of a 3x3 system. So what we are saying here is that in the constructor, you need to establish a connection between the top row and the source site, and you need to establish connections from the bottom row cells to the sink site. All right. Now, how do we do this? So this is where the encode method is going to come in handy. So for example, if you want to connect this site here 1 to the source, then you would make use of the union find data structure. So you would say the union find object, right, dot union, and you need to give it 2 arguments which are site IDs. All right, So how would you get hold of this site? Well, it's the site that corresponds to this cell. So you would simply say encode 00. Okay, so encode 00 takes a cell information, so 00, and turns it into a site ID, which is 1, and that we are connecting to the source, which is represented by 0. Okay. How would you connect this guy to the source? Well, it's the same idea. So you would say union find.union encode 0 2, which is the cell that has 3 for site ID, and you would say the source, which is 0. Okay, now this encode method is going to return 3 here. All right, so that's how you do it. So just use a simple loop to connect all of the cells of the first row to the source site and all of the cells in the last row to the sink site. Okay. So, and once you have done that, then this is how you can think about how the top row and the bottom row is connected to the source and the sink. Okay. So now let's talk about some of the other methods in the API. So how do you implement the open method? So open gets 2 arguments, I and j, representing a cell in the percolation system. So you need to open that cell if it has not been opened yet. Okay, so if it's not already open, open it. And then you need to increment the number of open sites by 1 because you just opened a cell. And then what you need to do is something very important. So you need to check if any of the neighbors to the north, east, west, and south of this of the cell that you just opened is open in itself. Okay, so if you opened ij, then simply look to its north, west, east, and south. And if any of those cells is open, then what you need to do is you need to establish a connection between the site that corresponds to ij, the one that you just opened, and the site corresponding to the neighbor that is also open. Okay, so let me repeat this. So let's say you opened a particular cell ij, look to its north, east, west, and south, and if any of those neighbors is open, then establish a connection between the site corresponding to ij and the site corresponding to that neighbor. Okay, and here again you would make use of the union find data structure to establish that connection, along with appropriate calls to the encode method. Okay, so that's open. What about is open? Is open is extremely straightforward. You're given an I and j, and you're supposed to simply return true if that cell is open and false otherwise. That's fairly easy. You simply consult the percolation system. Is full, the same thing. You're given 2 arguments I and j, and you're supposed to return true if that cell is full and false otherwise. Here, this is how you're going to implement this method. A cell ij is said to be full only if it is open and if the corresponding site is connected to the source site. Okay, so think about this carefully and see why this makes sense. So for a cell to be full, meaning when you pour something at the top of the percolation system, for it to get to the cell ij, that cell needs to be open to begin with, and it has to be connected to the open sites in the top row via a path of open sites. And if you look at it from the union find data structure standpoint, what it translates to is that a cell is full if and only if it is open and its corresponding site in the union find data structure is connected to the source, the virtual source site. Okay, So that's the idea that you would use to implement is full. Number of open sites is trivial. You simply return the variable that stores the number of open sites. And then percolates is supposed to tell you whether or not the system percolates. Well, when does the system percolate? It percolates. Again, this question is very nicely answered when you look at things from the union find standpoint. So in the union find data structure, if the sink virtual site is connected to the source virtual site, then we say that the corresponding percolation system does percolate, right? And if the sink is not connected to the source site, then we say that the system does not percolate. Okay. And I hope you appreciate how easy this problem becomes when you're using the union find data structure to answer this question. Because without the union find data structure, what does it take to tell if a 2D system percolates or not? Well, it takes a scan of the bottom row. So you have to scan the bottom row and see if any of the sites in there is full or not. Okay. Whereas if you map the percolation system to union find data structure with these virtual sites for source and sink, then the problem is fairly straightforward. You simply check the sink site and see if it is connected to the source site or not. Okay. All right. Now, using these virtual source and sink sites does help us in implementing the methods from the percolation API fairly efficiently, but it doesn't come without problems. It does introduce this problem of backwash. Okay, so let me explain what that is. So let's say you have a 3x3 system, which is what is shown here, and let's say you open the cells in this order. You first open 0, 1, and then you open 1, 2, and then you open 1, 1, and then 2, 0, and then you open 2, 2. When you do that, the system immediately percolates because you have a path from of open sites from here all the way to the top. So something that you pour here does get to the bottom. So the system percolates. But since we are using this union find data structure along with these virtual source and sink sites, what happens is since we have connected all the open sites in the bottom row to the sink site, when you open this cell, right, gets flooded. Okay, and you can see that here. It's in this sort of like yellow color. Okay, but on the percolation system, in the percolation system, 2, 0 is really not a full site because something that you pour here cannot get to the cell 2, 0. But because of this approach that we used with the virtual source and sink sites, we have this problem of backwash. Okay, so the stuff that you pour here comes here all the way to the sink, and then it floods back into this open cell. Right, so this is the backwash. All right, and that is what is mentioned here. So this cell 2, 0 is technically not full since it is not connected to an open cell in the top row via path of neighboring open cells. Okay, but the corresponding site in the union find data structure is connected to the source, so it is incorrectly reported as being full. Okay, as indicated by this yellow color here, and this is the backwash problem. Okay. Now, in order to receive full credit for this problem, you need to address the backwash problem, and it's a very a nice trick that you play to solve this problem, right? So think about it. But keep in mind that you are not allowed to change the API for percolation or the API for union find for that matter, right? So you're not allowed to change those guys. And yet there is a very nice way in which you can solve the backwash problem. Okay? So it just takes a little bit of thought, but it's very interesting. So challenge yourself into solving that problem. All right, so now let's talk about the second problem, which is estimating the percolation threshold. So in order to estimate the percolation threshold, what we need to do is create a data type that is called percolation stats. right? And that needs to support this API. So it has a constructor that takes two arguments, the size of the percolation system and also capital T representing the number of experiments that you need to perform in order to determine the percolation threshold. Okay, and we'll talk about what an experiment is. And then once you have an object of type percolation stats, you can get the mean of the percolation threshold, okay, from all from the T number of experiments. You can calculate the standard deviation of the percolation threshold, and you can also calculate the low and high endpoints of the 95% confidence interval. Okay, so it's a very simple statistics, right? So that's the API. So let's talk about how you implement this. So for instance variables, you're going to need two things. You're going to need capital T, okay, that stores the number of experiments that you need to perform in order to determine the percolation threshold. And then you also need an array called P, one-dimensional array of primitive doubles, right? And this array is going to have size capital T. And what is it going to store? It's going to store the percolation threshold from each experiment, from each of the T experiments, okay? So those are the instance variables. Now let's talk about how you implement the constructor. So it's basically the constructor where you do bulk of the work. So here you need to perform capital T experiments, right? So you need to perform a certain experiment capital T number of times. And what does each experiment involve? Well, it involves creating an n by n percolation system. So this is where you will use the percolation data type that you implemented in problem 1. So create an n by n system, and then until the system percolates, so until the system percolates, the system that you just created, until it percolates, choose a cell ij at random. So I needs to be a random value, j needs to be a random value from appropriate intervals. So choose a cell at random and then open it if it is not already open using a method, a suitable method from the percolation API, right? So open it if it is not already open. And then what you need to do is just figure out the percolation threshold for that experiment as the fraction of sites opened. Okay, so you keep opening, and at some point the system is going to percolate. So how many sites did you open? Well, divide that, the number of open sites, by the size of the system, which is n squared, and that is going to give you a percolation threshold, which you store in P for that particular experiment, little t, all right, where little t goes from 1 all the way up to capital T. So you're performing capital T experiments. And for each experiment, you calculate this percolation threshold and simply store it in this array, okay? And once that is done, the rest of the methods are trivial. So in the mean method, simply calculate the average of the values in P. In standard deviation, calculate the standard deviation of the values in P, okay? And then for the low endpoint of the 95% confidence interval, simply calculate this expression and return that value. Similarly, for the high endpoint of the confidence interval, calculate this expression and return that value. So these are all extremely straightforward. And now here, in order to calculate mean and standard deviation, you really don't need to do much work at all. Consider using a suitable method from stdstats. All right? Okay, so that's that. Now, a few things that you need to keep in mind. Now, the data directory that was part of the zip file that you downloaded for the project contains some sample input files that you can use to test your implementation, okay, of the percolation data type. All right, and along with the input files that you see in the data directory, you will also see some output PNG files that shows what the desired output is. Okay, so you can run your code against these input files and you can compare your result with the expected output, okay, which are given to you as .png files. So try to run your program against as many files as possible from this data directory. Okay, and then we also give you a couple of visualization clients. So the first one is and we strongly encourage you guys to use these clients to test and debug your percolation data type. Okay, so the first visualization client is Percolation Visualizer, that takes as command line argument the name of a file specifying the size and open sites of a percolation system. All right, so it's one of the files that for example, one of the files from the data directory, right? So that's taken as a command line argument, and it simply visually reports. You can visually tell if the system percolates or not. Okay, so it's a very nice program that makes use of your percolation data type to check if an input system specified as a text file percolates or not. Okay, so it's a very nice program that you could use to test and debug your code. Similarly, there is another visualization client called Interactive Percolation Visualizer that constructs an n-by-n percolation system where n is given as a command line argument. Okay, and then what you can do is you can interactively open sites in the system just by clicking on them. Okay, so when you run this program, you will see with an input of n, you will see an n-by-n percolation system on the screen, and then you can just interactively open sites. Okay. And then you can visually inspect whether the system percolates or not. So again, a very nice program that lets you test and debug your percolation data type. So it's strongly recommended that you run these programs, right? And then in order to receive full credit for each of the problems in this project, your solution needs to implement any corner cases that are listed for each problem. And they also need to meet the performance requirements that are stated, right? So pay attention to both the corner cases and performance requirements. And then in the report that you write, make sure that you use the given template, which is part of the zip file, and do tell us about the time that it took for you to solve the work on the project. Give us a short description of how you approached each problem, and mention any issues that you ran into and how you resolve those issues, and do acknowledge any help that you receive, right? This is extremely important. So if you receive help from anyone at all, do mention that in the report. And then also do tell us how much you liked working on this project, all right? And what you learned from it and so on. And if you don't, and if you didn't like this project, then tell us about that too, right? Okay, now before you submit your code, make sure that your solutions meet the input and output specification, and the way you can do that is by running the run tests script that is given to you, and you can run it using this particular syntax. If you don't specify any argument, it's going to test all the problems, and if you do specify a particular problem or a list of problems separated by commas, then it's those problems that are going to be tested. Okay, but do use this command before you turn your files in. And then also make sure that your programs meet the style requirements, and you can do that by running this command on the terminal, check style and the program name, right? If you don't meet the style requirements, you're going to lose some points for that. Okay, so please pay attention to this as well. And then finally, make sure that your reports are not too long. Make sure that they do not contain lines that exceed 80 columns, very important. Otherwise, it becomes very difficult for us to read it. And then make sure that your reports do not contain spelling mistakes or grammatical mistakes, all right? Okay, so that's all for this video on the percolation project. So I hope you guys have fun working on this project. Thanks for your time.